President of Lesman Instrument Company. This is a re-recording of the session that we tried to broadcast earlier, and because of a audio technical difficulty, we had to cancel that session. So we're recording it now so that you can listen to it at your leisure. Thank you for taking time out of your busy schedules to listen to our presentation, Approaches to Process Control, presented by Lesman's own Dan Weise. Today, Dan's going to answer some questions like, what's the difference between a PLC, a PAC, a batch controller, a single loop controller, DCS, SCADA, and all the other alphabet soup that's out there. After today's session, it should all make a little more sense. Dan has been involved in all facets of process instrumentation since 1978, from sales and commissioning to service and support. He's a longtime member of ISA and has been with Lesman since 1988. Dan is the primary contributor to our Process Solutions blog and routinely travels to Lesman customers to help solve their instrumentation problems and get the most out of the technologies they purchased. In Dan's own words, he's the guy who reads all the manuals that nobody else does. In Lesman's customers' words, he's the trainer you call if you want to cut to the so what of instrumentation. He makes it easy to understand. If you have any questions, please feel free to email them into us at either miked@lesman.com or danw@lesman.com. With that, I'm going to turn it over to Dan.
Thank you, Mike. I want to start out with a couple of explaining the conventions I'm going to use in this. I use the word HMI in 3 different ways. One is just for the display that you get on any kind of device out there. You'll see in the upper corner up here, there's the set point in the process variable. It's digital numbers. That's the HMI for that little controller. Then there are the HMI panels that go in, and they're graphical panels. And you can see on this one down here, there's a tank with push buttons, soft push buttons, and that kind of thing. They're everywhere out there in the control world. And then there's the category of software called HMI software that does supervisory control, has the tools for building graphic displays, does data acquisition, and builds an historian database so that data can be trended. You can read the examples down there. There must be 100 different products out there that fill the category of HMI software. The other thing that I want to distinguish between is programming and configuration. With programming, you have to know a language that has a set of rules and a syntax. You have to develop your own logic. You start with a blank slate, a blank page, and build it from everything, comments and everything. An example of this is structured text. In comparison, there's configuration. Configuration always has a menu. You use some kind of menu navigation technique, typically push buttons. You get to a given parameter, and you select from a variety of choices what you want that parameter to be. And that's menu-based configuration. Why does this matter? Well, when you're trying to deal with control strategies out there, part of the thing that you have to consider is what you can bring to the party. We got a lot of different people out there, or a lot of different companies that can bring somebody to the party that can configure, but they don't have programming skills. You got to figure also that tech support will usually assist in menu selections, but they're not prepared to advise on programming. Now, programming skills can be brought to the party if you don't have them in-house. Systems integrators do this for a living, but it's one of those trade-offs you got to configure when you're looking at control selection. An example that's not a control, but a recording, is that in 1992 or thereabouts, the prediction was made the recorder market will be gone by the year 2000. The reason for that was DOS PCs had come into the marketplace, they'd been accepted by business, and the assumption was that HMI and SCADA packages on a PC would do what recorders do and would just drive the recorder market to zero. 25 years later, we're still selling hundreds of recorders annually. Why? Well, the primary reason is that recorders don't lie, and people still recognize this. But the second reason is that people realize that they can make incremental changes to a recorder. They can add a point, change the range on it, do those kinds of things without having to call on a third party to make the changes for them. So it's something that they can maintain themselves. In anything you got to do out there, you got to match your resources to the task at hand. Any control strategy includes the basic field sensors, control hardware, final control elements, and the driving force in looking at this stuff is that any company has to be competitive, and you got to automate to cut costs. But nobody's resources are limitless. Everybody out there has to deal with budgets. You got to deal with the people that are going to interface with this stuff. You got to deal with the cost of ownership. So the control strategy that you pick has to fit what your resources are and what you can bring to the party, or what you're willing to hire out there to bring something into the party. So let's start at the basic control loop concept, because that's what we're doing throughout automation. A control loop is something that you got to control to a given condition, a set point. The control loop has to measure the process, it has to make a decision, and it has to create an output change. That's what control is. In measuring, we've got transmitter, sensors, and analyzers, all of which collect data out in the field. They transduce some physical phenomenon, make it into either a mechanical or an electrical signal that can be monitored by the controller. The process variable is the generic term for all those things that we're measuring: temperature, pressure, flow, level, pH, relative humidity, whatever. I call it what you got. In other words, that's the thing that's out there. That's the state that it's in at this moment. In this little controller up here, you'll notice that they use the letters PV for process variable, because on the controller, it doesn't have engineering units that you can actually put up there. So they just tell you it's the PV on the top, and then on the bottom is the SP, or the set point. The set point is what you want it to be. On this little round controller up here, it's a little black arrow. The process variable is a little red arrow. And then again, on the controller, they just put it up there as SP on the bottom, so that you can tell the difference between the process variable and the set point. So what the controller does is it reads the measured process variable, what you got. It knows what you want because you put a set point into it, compares those two things. Then it makes a decision based on that comparison. Do I hold steady, increase, or decrease? It makes the decision and puts the data out there, or changes the output. By the way, in the safety world, they call controllers logic solvers. We're going to get to that further on down the road down here. The output goes to something in the field that makes a change. There are AC drives, there are contactors, valves, motors, SCRs. These are all the things that actually make changes to the process. They put energy in, or they change the amount of mass in the process. The most basic form of control is on-off control. It's two states. It's either on or it's off, binary. It's simple. There's no tuning, but you'll see on this graph down here, the black line here is what we want, and the green line is what we actually get. And you can see that this process variable just oscillates up and down. And the difference between the top point and the bottom point is the deadband. That's the gap between when the output turns on and turns off. You have to have it with on-off control. There's no way of getting around it. It prevents the output from chattering or just sitting there oscillating and turning on and off real quickly when it's right around set point. There can be wide deadbands, pump up or pump down operations use wide deadband, alarms, or some control uses a very narrow deadband. On-off controllers come in all shapes and forms. You can see some are mechanical here. We got the rotating paddle for level, got the capillary and bulb for temperature, you got the bellows on this differential pressure switch, and then some of them are electronic. There's the safety controller that shuts down the fuel supply to a burner, a pH controller that's on-off for pH control, and a little temperature controller that's on-off. There's expanded on-off control. These little devices just don't turn the pump on or off. They'll actually alternate between pumps. You'll see in this diagram over here, pump number A is on, B is off, and then it alternates next time so that B is on and A is off. And then there's also a feature where you can stage the pump so that if A can't keep up with the demand, B will come on to assist. So that's a form of expanded control. Another form of expanded control is batch control. With batch control, you got a vessel. Typically, it's just like cooking in the kitchen. You have to fill the vessel with very specific amounts of material from a recipe. And the technique is the operator enters a preset value, which is the set point, which is how much you want it to fill with. They hit the start button, and then the batch controller does the rest of the work. Reads the output of the flow meter, totalizes it, shuts off when the total is reached. Well, a lot of times there's what they call a dribble or a bleed option. So when you get to about 90% of that number, you operate a second smaller flow line with a solenoid valve that dribbles the last part in so that you can get a very accurate total going into it. Why do people buy batch controllers? Well, primarily because the thing we always hear is make it easy for my operators. They want it easy to train the people because they want as few keystrokes as possible. They want it local. They want one on every vessel so that the operator can't confuse which controller goes where. You're not on an HMI screen picking different things. And they can be commissioned without having an engineer show up to do it. They're basic batch controllers in a box. To summarize why people use on-off control, basically it's simple. It works well enough. I've got 4 of them in my home. I've got a gas furnace, a sump pump, a well pump, and my toilet tank all work on-off control. And they're very affordable. On-off generally costs less than modulating control. And it can be enhanced, as we saw with the pump control or with the batch control. It can be enhanced with electronic logic. So you go, great. But the problem is when we make our stuff, we can't have that constant oscillation. We can't have the overshoot, undershoot, overshoot, undershoot. You know, if it's essential that I have straight line control, what do I do? Well, for straight line control, there's something called proportional control, typically using the term PID control. And for those that might be new to this, the straight line here across the graph is the part that we're dealing with. And instead of oscillations, once we've come up and knead into our set point up here, we have straight line control. PID does this by modulating the output. Modulating means to incrementally change the output. Instead of being just full on or full off, 0% or 100%, you get intermediate settings on there. The incremental response provides just the right amount rather than too much or too little. We typically do this with a 4 to 20 modulating output signal, and we drive something like the actuator on a valve so that the valve will give us something like 62% output or 39% output rather than the on-off control of 0 or 100%. How does PID work? Well, PID looks at the error, and the error is the difference between what you want, the set point, and what you got, the process variable. It does a subtraction. The goal is to have 0 error when the process variable is the same as the set point. PID has 3 modes. The P is the proportional gain, where the response of the controller is proportional to the size of the error. The I is integral time, and by putting a time factor in there, it accounts for how long the error has existed, and it attempts to correct for that. And D is derivative, that accounts for how fast the error is actually changing in real time. Sometimes you don't have PID, sometimes you have P or PI. A P is a proportional only controller, and the classic example is a mechanical pressure regulator. Ideally, when you crank down that screw to get a given pressure output, it will hold that pressure at all flows, but the nature of proportional only control is that it has something called droop. And you can see that on the exaggerated diagram over here. The little red X indicates where the actual output pressure is in relation to the set point, but you'll see that it falls off as the flow increases over time. You can see that it gets lower and lower and lower, and the error gets bigger and bigger and bigger. That's just inherent in a proportional only controller. There's no way to get around it. But that's what the I is for. The I is the reset term that corrects for this droop in something they call PI control. It does that by integrating the error and making an adjustment for it. The D term is derivative or rate, and it looks at the rate of change of the error. And what it does essentially is, as a signal is approaching set point, it backs off more rapidly so that it prevents overshoot. Or on the other hand, if you're at set point and there's a load change and the process variable drops off, it will accelerate the output response rather than just waiting for whatever the proportional response would be. So PID sounds great. It can give you straight line control, and everybody wants to know what's the catch. Well, the catch is the controller has to produce, the key word is the appropriate response to the error. In other words, there's going to be so much that's the right amount to give the correction needed. Not too much, not too little. You get the wrong response or the wrong factor, it can actually oscillate or be sluggish. We see on the left-hand chart here the oscillations, winging, getting bigger and bigger and bigger. That's where it's chasing itself. Or the other hand, where it just never really quite gets up there because it's just a sluggish response. So the key here is tuning, and tuning relates to a process's inherent capacity. The capacity is the ability to absorb or release energy or change mass. And the goal of tuning is to match the controller's response to what the process capacity is. So every controller has numerical terms for the P and for the I and for the D. These are numbers that the microprocessor uses to calculate the response, which is the output. Everybody wants to know what the numbers or the values are to put in for the P and ID, because they can be a range of numbers, and the manuals don't give it, and there's a reason for it. We don't know, because every process is different. It's not like we're withholding secret information here. It's just that it varies from process to process, and it's unique to a given process. Now, there are rules of thumb out there. The particular process control loops generally have a characteristic that describes their capacity, and the little chart there gives those. The problem is, and I ran into this the very first time I ever tuned the control loop, was that it was a way over capacity gas-fired burner, and I ended up with a 650% proportional band, 2 seconds of reset, and no derivative, which is exactly the opposite of what temperature is on the chart there. That actually describes a flow loop to a T, but it's because it was a gas-fired loop that was way over capacity. They could have used a burner that was a tenth of that size and done the job. So you get in these situations where the rules of thumb might not work because the capacity, the general capacity isn't what the process capacity actually is. So the question is there an alternative to trying to figure this all out on your own or learning how to tune a control loop? The answer is yes, there is. You let the controller do the work. It's called auto-tuning. Most PID controllers out there nowadays have some form of auto-tune in them. The little graph there shows actually Honeywell has 3 different styles of AccuTune. You can pick the one you want. There's demand, which means you actually push a button and say auto-tune at this point, and when it does it, it's done, and that's it. It's finished. Well, at one extreme end, there's all-in-one proportional temperature regulator. This is actually Grandpa's technology, but it works. You can see here there's a capillary here with a bulb on it, and that is a sensor into the process. There's a screw point down. There's a screw adjustment on here for the set point adjustment. There's a spring in here and a diaphragm. So all this works together to actually give you proportional modulating control through the valve at the bottom down here. And you go, why would anybody use something as antique as that? And the question is, you don't need electric power for it. There are a number of places that have a steam line within 50 feet that they can use to get their heat, but they don't have any electric power there to run an electronic controller or they might even lack instrument air out there to drive the actuator on the valve. So there are reasons why people still buy this kind of stuff. Basically, though, there's a whole market out there of single loop controllers that do PID or on-off control, depending on the model. There are different sizes, as you can see from the graphs on the side. There are the pictures on the side. There's a whole range of capabilities. The one at the top is really a temperature-only controller, and the one at the bottom here is a full-blown process controller. The key to these is the HMI, the means that you interact with it and it tells you what's going on, is built right into the thing. There's nothing to program to get the HMI working. When you plug it in, the HMI fires up and it's just there. Most of these, in fact, 98% of them or 99% of them are menu configured. There's no programming involved. The one exception is the one on the bottom down there, the process controller. There is software that you can use to program it, but if you don't want to do that, this little door on the front flips down and there's some buttons and a knob under there that you can use to program it right from the front panel. There's a category of enhanced controllers called set point programmers. A lot of batch processes require some kind of recipe So these are recipes that you have to run through in the batch. And these devices do the control, plus they hold a whole set of recipes or profiles. So the operator walks up, picks a recipe, and runs it. So it's a packaged deal. Again, the HMI is built right into it. The wiring's on the back. It's a packaged solution as a set point programmer. There's a whole bunch of types of control that single loop controllers handle. You can read them on the list there. But I'm not going to run through in detail just because of the time limitations that we've got. Got questions on it? Please send me an email at danw@lesman.com. So in general, people say, well, why do people buy single loop controllers? Again, there were death notices published in the trade journals in the early 1990s saying PLCs are going to replace single loop controllers. And yet today, even with the people that use PLCs, we frequently walk in and we'll see that they're doing a pressure and a temperature control with modulating outputs with standalone temperature controllers or single loop controllers, and they'll feed that data back into the PLC so the PLC knows what those conditions are, but then they do other discrete operations of the PLC. And the question is why? Well, it's because of what single loopers offer. It's the loop solution in a box. You get your local HMI that doesn't have to be programmed. You get the dedicated PID functions. It's basically simple push-button operation. Changing the set point is a breeze on any of these. Another big thing is they have universal inputs. Most PLCs have cards that are either thermocouple cards or RTD cards or analog cards like 4 to 20s. You can't, an analog card won't take a thermocouple. Most of these single loop controllers have universal inputs on them, so it doesn't matter what you got out there for a signal coming in from the field. They typically have alarm outputs, and you put all this together, and there's still a big marketplace out there for single loop controllers because it fills the bill. Why use anything else, actually? Well, the big thing is the number of loops, because what the number of loops creates is the need to manage it. You need more data, and you need the data displayed better than just what a whole bunch of these little things are with numbers on the front of them. So the step up from single loop controllers that everybody knows about is typically when you get into the PLC world with the packs and this kind of stuff is where you separate the HMI for the controller. The control is typically blind. It's done on a rack with modular control. It's in the panel and it's blind. So because it's blind, we got to put something on there to be able to see what's happening. That's the operator interface, the HMI. That's classically either a panel HMI with graphics or it's a PC monitor that talks to the control system, which is running through a PC somewhere. And the big deal here is we've got customized display elements that could be programmed with the development software, and everybody knows a picture is worth 1,000 words. You can tell a lot with a picture that you just can't do with just plain numbers or words. So there's far more flexibility in presenting the data with the HMI. So when we're into this world, we have PLC control. Now, original PLCs were really just discrete I/O, but in the last 15 years, most PLCs have adopted some form of analog control. They're always rack devices with modular I/O. I shouldn't say that they're shoebox PLCs out there, but basically they look like the one on the bottom of the screen down there. They're blind. I mean, a PLC itself is blind. It doesn't have, it has little diagnostic LED indicators on it, but it doesn't really give you any process information. They can be networked, which you have to do because now you want to go out to an HMI somewhere and give it the information and let the HMI feed back because, again, the HMI is where people are going to do the supervisory control. They're going to put in their set point. They're going to make their supervisory decisions from the HMI. They're everywhere. It turns out it's not our strength because they're basically discrete control or discrete manufacturing devices. Instead, we get involved, we Lesman get involved with the PACs. PAC is a process automation controller. It's modular. You can see down at the bottom down here, it looks just like the PLC on the previous page there. So it's got the modular I/O, but it's process-based, not discrete-based. So it has slower scan times by at least an order of magnitude, but it's deterministic so that you're guaranteed that you're going to get a throughput at a certain rate, which is not always true of a PLC. As you put more and more rungs in the PLC ladder logic, you can actually affect the scan rate. That's not true with a PAC. PAC has a fixed scan rate. They can be networked like PLCs can, again, because you have HMI panels, and you got to get your data back and forth from the HMI. Like PLCs, they have redundancy, power control, networking, and this is one of the strengths that we work with is the PAC. The implications, by the way, going back to resources of modular control, is that typically you now have two software packages to deal with because these are programmed, they're not configured. You have a control development software package and you have an HMI development software package. So there's the people that are going to do this are going to have much higher skill set typically than the people that just configure the individual boxes, loop controllers. The other thing you got to be aware of is that when you start doing this and you're talking over a network, like you can see all these little purple and green and blue lines out here, the communications network, tie all this stuff together. There is some networking skill that's involved in this as well. So people buy packs because basically there's too many loops for standalone controllers, but you want to be able to manage this data. And the HMI gives you the tool to manage the data, gives you your picture or your view into what the process is doing. There are several things, by the way, that packs do that PLCs don't do. They always do auto-tune. They have set point programming built into them. They have things like actuator drive function blocks that just drive actuators directly without any external logic that you have to build. They always do the higher level communications, and they can do the stuff like PLCs do, which is redundancy in the networking. Then there's a category of SCADA control. And SCADA is really a word that has a lot of different meanings out there. I've heard it used, I just collect lots of remote points from remote RTUs. An RTU is a remote terminal unit. It's a box that has some I/O in it and then communications out. Typically, at one time, if data came over a phone line, you got it with SCADA. That was just sort of a definition for that. A lot of times, HMI software packages, something that I would just call HMI, is also called SCADA. And also there's a term data concentration where you're trying to bring a whole bunch of data into a small spot, and I've heard people call that SCADA. So I'm going to use it sort of like the little diagram on the right here where you get a bunch of RTUs out there and then they report into a basic MTU and then you get that data into your SCADA software or your HMI software. SCADA software is typically supervisory because you're sending out control information over a control link to a remote spot. So why would people pick SCADA? Well, it's basically the topology. If the points are really spread out geographically, that's where SCADA shines because SCADA puts a lot of emphasis on the communication on this stuff here between the HMI and the data acquisition system and the MTU. This is where SCADA, and also between the RTU and the MTU. They've got a lot of effort in that isn't always into just plain HMI stuff. The other thing is that there's a particular feature called sequence of events alarming. It usually is associated with a millisecond timestamp so that people can tell exactly what the sequence of alarms were. And that typically is a SCADA feature that isn't always as emphasized in ordinary HMIs. Then we get up to DCS control. It's the distributor control system. It's the total integrated control solution package. You do not mix and match an HMI to a controller like you can with a PAC or a PLC. On either of those other ones, if you want to do brand A hardware controller on brand B HMI, that'll typically work. But you don't do that with a DCS. It's server-based, and because it's server-based for everything, it easily connects to enterprise-level software, which is a big deal out there because the business people want to interact with all of this as well. And that's where some HMI software shines and other HMI software sometimes has holes in it. They do some really advanced control algorithms that just aren't out there for the PLCs or the PACs. What you also find in DCS control is you can have total ability to program your own control loops. You can do that with structured text or the other languages that they bring to the party. Why DCS control? Well, basically, it's sophistication because where they're typically used, which is in continuous process operations, the continuous process stuff makes commodities, paper, gasoline, steel, where it can be very expensive to try to differentiate between the commodities. Like when I go to buy gasoline, I'm just looking for regular at the lowest price. I don't believe that Shell's any better than Mobil. Okay? So in that field, the competitiveness comes from being able to reduce your production costs, and that's where DCS really shines because it gives you so much information. And the other thing is the software apps that are available at DCS level are absolutely phenomenal. I'm going to use an example here called Control Performance Monitoring. This is an add-on, tack-on package to DCS control. And what it does is it monitors all these assigned processes out there. It gives you two levels of response. Level one, it just shows you what all this raw data is. It tabulates it. So you get bar graphs or trends to see what's happening. The real key, though, is that it prioritizes what's happening out there, making decisions on it, and then actually recommends remedial action. So here's what it looks like. This is the performance assessment, which is the bar graphs. It just sort of tells you what's happening out there with numbers and percentages. But here's the real key. When you come into the expert guidance help page, you come down here where the recommended action says check and repair this control valve. And then it actually gives you a procedure for checking it and what you should see and what the root problems could be. Because this really impresses me, because we've lived with this whole phrase, meaningful diagnostics, for decades out there. And meaningful diagnostics generally means, when the vendors use that term, it means a whole bunch of data sitting there. Okay? And the question is, well, what do you do with that data? And this was driven home yesterday on a forum. And the guy wrote on the forum down here, you see, a manufacturer of valve and actuator specs a life at 2 million cycles. They then define a cycle as 0 to 90% movement. How about a case, in his case obviously, where the valve sits all day oscillating at 50 to 60%? What then constitutes a cycle for preventive maintenance purposes? Should we integrate the movement over the time period and divide by 90? You want some thoughts on this. It's been sitting out there and nobody's responded because probably, I don't know, nobody knows. Well, actually, some people do. The people that do DCS stuff have been looking at this stuff for over 3 decades right now. And they've got background on it, and therefore, somebody sat down and put together an application package, that control performance monitoring, where it'll actually make decisions and recommend it rather than just knowing, I've got this data. I oscillate at 50 to 60%, and it does this all day long. What do I do with that? How do I know when my valve's worn out? Well, control performance monitoring is going to make recommendations on that kind of thing. I'm impressed by that. You got to be aware, again, when bringing resources to this, it's sort of like the other stuff where you got to have some networking skills. And this is at 2 levels, because the platform communications is largely Ethernet network, and also the field bus stuff that you get into with DCSs, foundation field bus, Profibus bus, or Ethernet IP. That is a different skill set than what the ordinary guy that works with 4 to 20 or 0 to 10 volts uses. You can see the guy in the picture down there using an analyzer to try and check out what's going on there. We're going to move into safety controls now, and safety generally has standards behind it. And the ones that might be familiar to our audience here are NFP 85 for boilers, 86 for furnaces, kilns, and heaters, and the 6511, actually the 6511 or 61511, whichever one it is, for safety instrumented systems. But this is where we're getting into things where things that can catch fire and blow up are actually, there are standards that define what should be done in order to minimize the risk of that happening. And before I get into that, I mentioned this in a previous webinar, and somebody said, oh, am I dealing with a safety controller here because I have a fail-safe or normal selection for my alarm and output relays? And the answer to that is no, that's just good design. A fail-safe relay just says that the coil is de-energized during the alarm state so that when the power goes off to the device, that it actually goes into the alarm state. And you can pick whether or not, on most devices, whether you want an output to be fail-safe or not fail-safe. And the little table tells you there what state is which. But this generally does not fall into the safety category. It's just good process control design. At one end of safety, there's something like the FM limit control. The FM limit control is out there on all these boilers and all these furnaces and kilns out there. It's required by NFPA 86. And by the way, with these standards, there generally aren't standards policemen running around out there that write tickets for this kind of stuff. What happens is if there's actually a problem where somebody's hurt, particularly, or somebody's killed, the lawyers get involved in this. And if the process doesn't meet the standards, then somebody's going to have to pay, because it will eventually they'll either settle out of court or go to court, because it becomes a liability factor. So companies are doing this to protect themselves from the liability of having accidents. So the purpose of the high limit controller is to prevent overheating and potential fire. It's not there to protect the load. It's there to protect the rest of the environment from a fault that could have the boiler explode or have the furnace catch on fire. It does not control the process variable, or the temperature. It just limits the fuel supply to it to shut it down if need be. FM controllers always latch out. It means that when they trip, somebody's got to go up there and manually reset it, because that means somebody's got to show up to acknowledge that there's been a problem. Safety systems this is just like any safety system. It's a secondary, independent, in some fashion, a redundant safety control, but it does not share the sensor, because the sensor's got to be separate from the process control one, and it's its own separate controller. The process controller doesn't do this. It's its own safety controller. We got burner management systems out there, and burner management systems have two aspects. This slide shows you the process aspect, where it actually does the process control, which is regulating the demand firing rate that supplies the BTU, gives you more or less heat. It can do air-fuel ratioing, monitor or control excess air. It's a classic control loop. Okay, this is the process side of BMS. The safety side of the BMS has all these FM-approved safety components in it. You got to do flame detection. Then you have single burner or multi-burner controls that respond to the flame detection and or a whole bunch of other signals out there, safety signals like gas and low high pressures. You got a whole bunch of gas train components, which some of them which are sensors. The safety shutoff valve is the final control element. Then you've also got the limit controller that we mentioned before as part of the safety burner management systems. Now there's been a change to NFPA 86 in the last 2 years, and it really opened the door to have SIL2 modular burner management controllers package the stuff instead of discrete components to go to something like you see on the bottom down here with modular control. Now you still need to have flame detection. You still need to have the sensors on the gas train and the safety shutdown valve, but the logic making decisions can be done modular, and as well you can do the process stuff in these kind of boxes as well. The big effect of this actually is that because this now looks like a PAC or PLC and it's got communications on it, you can take the data out and you can put it into an HMI. There's a little example on the side here where you can see all the different components for the gas train and all the stuff that's out there. So this is a huge advance forward to giving you more information so that you can manage the burner train. A step even beyond this is safety instrumented systems, widely used in the chemical process industries. Again, insurance and liability is the driving force behind this. And they got the ISA and the IEC standards to cover how you analyze it, what you do for designing, and how you actually come about with factors that tell you what you're going to need in this in order to minimize your risk. And a lot of people have probably heard about SIL certifications. The higher the SIL certification, or the SIL level actually, the greater the impact of failure and the lower the failure rate that's acceptable. The one out there that people talk about, well, do I need SIL 3 is the big question out there. And I can't tell you that. The vendor is not supposed to tell you what you need. You have to go through what they call a HAZOP, which is an analysis process in order to determine what level of SIL is required to reduce the risk to that which is acceptable. The goal of all safety instrumented systems is to bring the process to a safe condition. And to do that, there are components that are either proven in use or SIL certified. And there are 3 agencies out there, FM, XCEDA, and TÜV, that can all certify devices to have a given SIL certification on them. And those are the field devices that sit out there. And there's also controllers and what they call logic solvers that are fault tolerant and have a lot of internal diagnostics to determine to make sure that they're actually operating properly. The whole system typically involves voting logic because a lot of times it involves redundant sensors. They got to determine which of these sensors are working, and if a sensor goes bad, throw it out of the mix so that you're relying on the remaining sensors as valid sensors. Widely used in chemical, gas, and oil, but when you read the trade journal articles, you see that safety instrumented systems are probably going to move into other industries as well. So that sort of sums up our seminar today, or webinar today. This is the recording one. So again, if you have questions, would you email them to miked@lesman.com or to me, danw@lesman.com. Thank you for attending.
Dan, thank you very much for